Dear students, welcome to the knowledge series. Here we are going to discuss on Dijkstra's algorithms example with respect to shortest path. You can see in the given figure there are 6 vertices, and let us consider this particular given network with some arrows to signify that each vertices are connected with an inside or an outside arrow. So let me put these notations with respect to an arrow. So we will consider some figure modifications. So let me put some arrows over here. So these are the arrows coming to vertex C. This is the arrow pointing towards the vertex B, and towards D these are the 2 arrows, and towards E let us put one vertex here, one arrow here toward this vertex, and one arrow here, and finally to this vertex F these 2 arrows. So our network is ready. So in this given network we consider A as our starting point. So we will consider this is the starting point and this is the destination. So based on this particular given vertex, we will follow certain steps, and in the initial steps we will what we are going to do is in the step 1 we will be assigning the weights as well as the cost. Weight is indicating all the vertex that we signifies as the weight, and those which is connected between the node to node, that is nothing but the cost of the link. Those things you are well aware about it with my previous videos. So here if you consider the vertex V with its own weight as 0 because it's a starting, so automatically we have other weights of the vertex B as what, 1 here, and this is 2 here. These 2 arrows are emerging out, and this is adjacent neighboring nodes, and thereby it's a direct path. But rest others we find that all the other nodes are not direct, all are indirect, so that's why its weight is infinite. So we put it as infinite here. So the very first things is that we identify the direct, and we put it as identify direct and indirect path from E. So this first part is over. That is what. Now our next step 2. Step 2 is what we have to look forward for relaxation condition. And about relaxation condition, you can see my earlier video where I have spoken about relaxation condition. So under the relaxation conditions we will go with the next step. What is the step 2? We will look for the node emerging out from A, and that is the neighboring node. Among the neighboring node, which is the which has the smallest weight. So we find that B is having a smallest weight. So we consider B as the shortest path vertex. So shortest path vertices, that is B. So with respect to B, we will look for the neighboring node of B, and the neighboring node of B is what is the distance with respect to A. So if we write A, B, C, we find that the weight is 1 plus 1, that is BC. We consider BC. The weight of B is 1 and the link between B and C is 1. So 1 plus 1, that is equal to 2, and that is the weight at where C. So at C the weight is 2, and that and the previous weight was also 2. So both are same. So there is no relax. So it shows that no relax condition is satisfied. Next conditions, it is what ABD. So let me put it as BD. If that is the scenario, what is B1 plus link between B and D is 3. So that is 4. That is the weight at D. So here you can see that weight at D is 4, it shows. So automatically 4 is less than the actual weight was infinite. So it is a relaxed conditions. So what we are going to do, we are modifying this infinite to 4. Next we go with ABE. So that we write it here as E. So here what is the weight? 1 plus link cost is 2. So that is 3. So 3 at E, and this is less than the previous weight was infinite. So this shows that there is a relaxed condition is there. There is a relaxed condition. So in the relaxed condition, what we are going to do, we modify this one with the new weight, that is 3. So now what are the different steps we have covered? We covered from A, we covered all the B's. Now we look for next among D, C, E and F, which is the smallest weight? Weight is C. So the next shortest weight. So I can put as the next smallest weight is our C. So let me put this one as 1 so that it is easy for understanding. So we go with next smallest weight. The shortest path vertex with respect to smallest weight is C. Now here we consider again what is we are going to consider from C to only 2 vertices, 2 links are emerging out to, one is to E and another to D. So we write it as CE. If we consider this CE, this is 2. This is 2. And the cost of link is 2 between C and D, that is equal to 4. And 4 is greater than 3. So it has no relax. So we can ignore. Next is C to D. When we consider C to D, it is 2 plus 1. So 2 plus the link cost is 1, that is equal to 3. And this is 3 and this is 4. 3 is lesser than 4. So this is a relaxed conditions. So what we do, we modify this one and by new weight, that is 3. Now next is what we go do. Now C is over, B is over. Now we have a D, E and F. Now where we will go, we have seen D is 3 and E is also 3 and F is also this one. So let us consider the third steps is that we will consider shortest path vertex. What is that is D. So under that condition, D from D to links are emerging out. So we'll consider D to F. So D to F shows that D is 3, F is 3, 3 plus 3 is 6. So 6 is what? 6 is less than infinity. So since 6 is less than infinity, so we will modify this one by new weight. So we rewrite this one as 6. Now what is the next one? We will consider D to E. D to E is how much? It is 3 plus 4, that is 7, which is greater than 3. So here it was relax, so here is no relax, so ignore. Okay, ignore. Now what is next? That is fourth one. The remaining is E and F. So among these things, E is the smallest. So we will take the condition E to F. What is the E to F? Its weight is 3 plus 3, that is equal to 6. So no change. So this completes all the vertices. So all the vertices of the shortest path has been completed. So we are seeing that this is 1 here, this is 3 here, this is 6 here, this is 3 here, this is 2. So with this we come to the end of the finding of the shortest path for this numerical problem. Thank you.